My graduation thesis focuses on weakly supervised video anomaly detection. The goal is to automatically analyze video content and locate temporal segments that may contain abnormal activities. The dataset used in this project covers 13 types of abnormal events, including robbery, road accidents, fighting, etc. It should be noted that the system mainly determines whether a video segment is abnormal, rather than classifying the specific type of anomaly. For each segmented part of a video, the model outputs an anomaly score between 0 and 1. A higher score indicates a greater probability of abnormal activity. After an anomaly threshold is set, any segment whose score exceeds the threshold is marked as a suspected abnormal segment. During data processing, the input video is first divided into a series of short clips. A pre-trained 3D ResNet 101 is then used to extract spatial temporal features from each clip. To process videos of different lengths using the same model, the extracted features are uniformly organized into 32 temporal segments. Each segment is represented by a 2048-dimensional feature vector. Therefore, each video is ultimately converted into a 32 by 2048 feature matrix. This representation preserves important visual and motion information while significantly reducing the computational cost of the subsequent anomaly detection model. The extracted features first pass through a feature projection layer, which reduces their dimensionality from 2048 to 512. The model then applies three one-dimensional temporal convolution branches with different dilation rates to analyze changes across different temporal ranges. A smaller receptive field focuses on sudden short-term changes, while a larger receptive field captures abnormal events that develop over a longer period. The outputs of the three branches are fused and combined with the original features through a residual connection. The model then performs top K segment selection based on feature magnitude, allowing it to focus on the segments most likely to contain abnormal activities. Finally, the anomaly scoring module produces an anomaly score for each of the 32 segments. The front end displays these scores as a bar chart and marks suspected abnormal segments according to the selected threshold. This is the video anomaly detection front end developed for the project. Users can upload either a video file or a pre-extracted feature file. After detection, the system displays the highest anomaly score, the average anomaly score, the peak segment, and the overall risk assessment. The bar chart below shows the anomaly score of each of the 32 segments. Red bars indicate suspected abnormal segments whose scores exceed the selected threshold. Next, I'll demonstrate the system using a road accident video, a robbery video, and a normal video. The first example is from the road accidents category. The video is approximately 40 seconds long, and the actual accident occurs at around the 17th second. The main abnormal interval detected by the model is approximately from the 11th to the 19th second. The actual accident at around the 17th second falls within this interval. Therefore, the detected abnormal region is generally consistent with the actual time of the accident. This result demonstrates that the system can not only determine whether an anomaly exists, but also use the anomaly scores of the 32 segments to approximately locate when the road accident occurs. The second example is from the robbery category. Compared with the first video, this video contains more noticeable scene transitions, while the robbery mainly occurs in the middle to late section. According to the anomaly score curve, although the scene changes during the video, the model still assigns higher anomaly scores to the middle to late section where the robbery occurs. This indicates that the model does not simply treat a scene transition as an anomaly. Instead, it combines human activity, motion changes, and temporal context from multiple neighboring segments to identify the abnormal event. Therefore, even when the video contains scene changes, the system can still locate the approximate time range of the robbery relatively accurately. The final example is a normal video. People appear and move through the scene, and the visual content changes over time, but no actual abnormal event occurs. The result shows that the highest anomaly score is only 0.119, while the average score is 0.047. The scores of all 32 segments remain clearly below the selected threshold. Therefore, the system classifies the video as low risk and detects no abnormal segments. This result demonstrates that the model does not produce obvious false alarms simply because people appear, move, or because the scene changes. It can effectively distinguish normal activity from actual abnormal behavior. The results from these three videos show that the system can uniformly divide videos of different length into 32 temporal segments and output an anomaly score for each segment. After an anomaly threshold is set, the system can identify suspected abnormal segments and approximately locate when an abnormal event occurs. In the road accident and robbery videos, the higher anomaly scores are generally consistent with the actual event locations. In the normal video, the anomaly scores remain low even when people appear and the scene changes. These results demonstrate that the proposed model has a certain ability to detect video anomalies and resist interference, providing a useful reference for the automatic analysis of surveillance videos.